there's a lot of terminology to get. It's a kind of new viewpoint on things. So it might take a little while to orient yourself to it. But there's no queries in the meantime. We'll just keep going. Okay. So we've looked at the definition. We've looked at a few examples. Matrices multiplying points in the plane, 2 by 2 matrices, in vertical matrices multiplying points in the plane. The dihedral group D4 represented through permutations of the vertex labels that acts on the set of vertex labels. And then we have these two examples which we'll, at least one of them we'll see again and again, self-actions. Actually, the group can act on itself through operations either exactly being multiplication or related to multiplication. And this one, related to multiplication, this action of conjugation is quite an important concept of a group acting on itself. And when we're able to kind of deconstruct and analyze this action of the group on itself through conjugation, we can tell a lot about the structure of the group. Get to these things called C-log theorems, which guarantee the existence of certain subgroups of the group based only on the size of the group, without knowing anything else about the structure or about the context, what the actual elements are. Just simply knowing that it's a group and that it has a certain size, you can immediately say there must be subgroups of a certain smaller size within that group. Okay, that's to do with the prime factorization of the size of the group. So nice connections to the number theory stuff as well. Okay. So we've seen the definition, we've looked at a bunch of examples. We now want to develop some of the initial theory of group actions. And there's a few kind of devices or concepts that we want to talk about. Okay. So the first of them is an equivalence relation. So what we're doing here is we're beginning to analyze, we're analyzing features, aspects of the action of G on X. We're back to talking abstractly. Just some group acting on some set X. Okay, we're going to analyze some of the features of it. So the action induces or gives rise to a natural relation. I'm going to get ahead of myself and call it an equivalence relation. We'll find out it's an equivalence relation. But first off, it's a relation on X. Okay? So this is this G equivalence. So we say, so if we have X and Y, two elements of this set X, we say X is G equivalent to Y. We write that as X tilde, and you put a little subscript G on the tilde. We won't use that notation a whole lot. We will use this concept a lot, though. So X is G equivalent to Y. What does that mean? Just want to make sure I set it up carefully. So Gx is equal to Y. So this, we write X is G equivalent to Y, written like this, to mean that there exists an element G in X such that Gx is equal to Y. Okay. So two elements in the set. We regard them as being equivalent. We regard X as being related to Y if there exists an element G that moves, if you want to think in a dynamic way, this element G, it moves X to Y. Okay? When you consider this little G as a function and you apply it to the argument little X, you get the value little Y. Okay? So in some kind of a way, some kind of mathematically meaningful way, G moves the element X onto Y. Okay? And so proposition 14.6 is what I let slip slightly earlier. So this isn't any old relation, this is an equivalence relation. Okay? So this is G equivalence. Well, yeah, in the name, G equivalence is an equivalence relation. Now, I'm guessing you would appreciate a quick reminder of what an equivalence relation is. Yeah? Or do you know? There's 3 conditions. Remember what they're called? Symmetry, reflexivity, and transitivity. These are nice properties that we look for in a relation. It makes relations very easy to understand. It makes relations easier to understand and study. So, i.e., tilde G is symmetric. So I might do them in a reflexive. Yeah. Symmetric, reflexive, and transitive. So what does this mean? Symmetry means for every x, y, x tilde y implies y tilde x. So if the relation goes one way, it goes the other way, automatically. If I'm related to you, you're related to me. Okay? So it's symmetric. Reflexive means for every x in x, x is related to itself. Okay, I'm omitting the subscript g of the tilde. According to the definition, I have a subscript g of the tilde to show that this relation comes in the action g. But I'm just going to drop that. Subscript g is all over the place. So reflexivity says every element is related to itself. And transitivity, this is the one about traveling through intermediates. So for every 3 elements x, y, z in x, if x is related to y, and y in turn is related to z, that implies, those two imply that the first x is related to the third. So this equivalence travels through intermediates. If I'm related to John, John's related to Jane, means I'm related to Jane. Okay. If that's always the case for every triple element, okay? That's what an equivalence relation is. So you must be able to prove this. Now, what kind of things can possibly feed into the proof of this? Well, it's the definition of G equivalence itself. So if we, at any stage, see, we have to prove these things, so we have to make this assumption x. We assume x is equivalent to y. We're going to try and prove y is equivalent to x. We're going to have to prove that every x is equivalent to itself. And we're going to make 2 assumptions here, x equivalent to y, y equivalent to z. We're going to have to prove that x equivalent to z. So how do we make draw these conclusions? Prove this for every x, and prove this based on that assumption. Okay, the only things that can possibly feed in are the definition of G equivalence, so the definition of what it is we're assuming here at the various stages. The fact that this is a group action, so properties 1 and 2 are going to feed into it as well. We'll have to be using those because they are what define a group action, so surely properties of group action are going to come from those. And maybe just some very basic things about a group, how the group operation works, how inverses work, etc. Okay, things like associativity of the group operation and so on. So those are the kind of things we expect to, even without engaging with the detail of it, but just from what we're at, from the kind of thing we're asked to do, those are the things we expect to see appear in the proof. Okay? And then, to prove this, or to, if in an exam you were asked to prove this, those would be the kind of initial thoughts you'd have before diving into it. You think, okay, well, this is the definition of equivalence relation. This is the definition of the relation itself. Okay, I know group actions defined like that. I just need to put all these things together. Okay. Well, let's take the reflexivity first. It's the one you take first in the book. So you let x be an element of x. If you want to conclude, remember in number theory we often put down the conclusions and then try to bridge the gap from the assumptions to the conclusions. So our conclusion we want is to say x is related to x. How can we ever say that x is related to x? Let's roll that one step backwards using the definition. It means we can find a group element. So I'll put a blank here. We can find a group, because look, x is equivalent to y means there exists a group element such that the gx gives you y. If I want to prove x is equivalent to itself, I have to show there exists a group element such that that group element applied to x gives you x. So I've got to fill that gap with a group element. Which group element?
The identity.
The identity. Why? By property 1 of group action. The identity element plays that role. There may be other group elements that play that role. If I knew a bit more detail about the group G, what these things actually were. But at least I know the identity element does that job. Okay. So if any x is in X, that implies e to the x is e times x is equal to x. That's just by the definition of action, left action, property 1. Okay. So that means it means it's reflexive. Yeah, that's good. Symmetry then would normally be the other one. So we would assume we've got x is equivalent to y. Because we're trying to prove this implication for every x and y. So we just treat x and y in general. Assume this bit, we want to conclude this bit. Again, you could do this nicely, filling the gaps. The conclusion we want is y is equivalent to x. Roll it back a bit. How we say that? Well, we have to show that there exists something that when you multiply it by y, you get x. So we want to fill that gap. What group element goes there? Okay, silence is the correct response because that reflects that, you know, there isn't really, there's no group elements floating about. We can't say it's the identity. We surely have to assume that y and x could be different. So it's probably not going to be the identity. But look, we've made this assumption. Assuming x is related to y, that means there's the existence of this element g. And not that it's going to be g that fills this blank, but maybe something related to g. So I should roll forward the assumptions as well using the definition. So that implies that there exists a g, exists an element such that gx equals y. Any candidates for a group element that goes there? Out of intuition.
Is it G inverse?
Is it G inverse? Is that a sensible suggestion, Rebecca, do you think? Just your instinct.
Yeah.
It is. It looks kind of sensible. If gx equals y, surely G inverse y equals x. Yeah, so it's correct. Okay, is it clear or do we maybe have to justify it a little bit? Could we justify it carefully, exactly, maybe, since this is the first time we're encountering this property, that if gx equals y, then G inverse y is equal to x. It's not explicitly stated there. But what is stated there, well, this thing about the identity fixing x, and then this relationship between multiplication in the group and compositions of these functions. Yeah, because, so that would imply, so let's try hit things with G inverse. So if I put G inverse down there times gx, that must be G inverse times y. That's surely correct. So I just apply G inverse to both things. Gx is the same as y. But of course, what's going on here? Here I've got a composition of these two functions, G inverse applied after G. Property 2 tells me that's the same as applying the function G inverse G. G inverse G is, of course, the identity. And by property 1, that would leave me with Ex on the left. So x on the left, x is equal to G inverse y. So yeah, G inverse is. So I'd maybe didn't leave myself quite enough room. So I'll say that this property, let's put square brackets on the right-hand side. That property implies that G inverse G applied to x equals G inverse times y, which implies that Ex equals y, sorry, G inverse times y Okay, so then that reduces to X by property 1, and you've got G inverse there. That's the thing filling the gap. Okay. So yeah, so there is, that's what we set out to prove. We set ourselves that challenge. Can we fill that gap with the group element? Yes, G inverse. So that's an excellent example of a case where, you know, when you put down the assumption, you're looking at the thing, you have to prove that your kind of instinct is correct. So it's a good instinct that if gx equals y, surely it must be the case that g inverse y equals x. And that's another example, that's another way of saying that the group action fits well with the structure of G. G, the function associated to G and the function associated to G inverse are inverses of each other, which is a natural thing to say. But maybe, you know, to rigorously prove it, we need a couple of equations and calling on properties 1 and 2. So I haven't explicitly stated which ones were there, but this was going there to there. What was that? That was property 2 from the board, and going there to well, that was just the group operation. G inverse times G is the identity, but going from then there down to there is using property 1 that EX is equal to X on the right hand side. So we know it's symmetric. Whenever the relation goes one way, x to y, it also goes back y x. Then we need transitivity. So for transitivity, we should assume x is tilde y and y is tilde z. Let's just try proceeding straight away. So that means there exist two elements, let's call them a G1 and G2. In G, such that G1x equals y. That's what it means to say x. Yeah, so just make sure you get the ordering right. So x is equivalent to what x is related to y means gx is equal to y. So there exists a G1 that does that and a G2 that sends y to z. Okay, we're trying to conclude that x is equivalent to z. No, let's do our bridging the gap thing. We're trying to conclude that x is equivalent to z. So in other words, we're trying to fill this gap of something applied to x equals z. So we want to apply some function to x and get z. We've got these functions floating around. One, when you apply it to x, you get y. Another one, when you apply it to y, you get z. So it's going to be the composition of those two. So that these two imply that if you do G2 on G1 of x, you get z. Just simply replacing y there by G1x. Put down property 2, so we're exactly coding property 2 there, just from right to left. That implies that G2 or G1 applied to x equals z. So that's by the definition of action. These here was by the definition of action as well. Okay, so this gap has been filled. G2, G1. G2, G1 is the answer there. So it is transitive. Show it's transitive. So that's the end of that proof. It's an equivalence relation. Now, always, the point about talking about equivalence relations are directly associated. Equivalence relations are partitions of the set. Okay. So since G equivalence tilde is an equivalence relation, the equivalence classes of it partition the set X. Here's your set X. Remember what a partition was. A partition is a subdivision of a set into a collection of cells or subsets for want of a better word, in a nice way, right? So that the collection of subsets covers the whole set X, okay? And there's no overlap between subsets. The subsets are distinct from one another. But when you take the union of them all, you've got the whole of the set X. Okay? So inside each set is a bunch of elements of the set X. Not necessarily all the same number. And what's true about these cells, if you look at one cell or subset, everything in there is equivalent to each other under this relation. What that means is, for every pair of elements here, there'll be some element of the group which moves that element to the other. Yeah? And moreover, if you do take any one of these elements and hit it, apply every possible function, every possible element from the group, apply it to this little x, it'll just move it around within this set. Yeah? It won't pop it out to here because these are different equivalence classes. Yeah? So any 2 points here, you can transfer from one to the other by an application of one of the functions from the set. And if you take anything from here, apply everything from the set to it, just hit it with all the group elements, that'll bounce it around across all of the other elements in the set. Okay? And those properties come from the fact that it's an equivalence relation. These equivalence classes have special names here. These equivalence classes are called orbits. Orbits. So the orbit of x, the orbit of a little x, and it's written, now you'll see it's like a funny O, it's kind of like a script O, a handwriting O. See it in the book there, right at the bottom of the page, 223 is the way it's written in that font. So it's meant to be like the same font as we used, that curly L we used for the cosets, the curly L we used for the Laplace transform last year. It's a script handwriting font. Sometimes people write it as like, something like that. It's a handwriting O. So it's an O, it's O for orbit, and it's associated to an element little x, so little x could be one of those there. And so the definition of it is, it's the set of every element y from x such that there exists an element g in the group G such that gx equals y. That's the definition of the equivalence relation. An x and a y are equivalent means there exists some element of the group G such that when you hit x with G, you get y. These are the orbits of x. And this very much ties in with this dynamic way of thinking about it, that the group acts on the set X because the elements move, the elements of the group move the elements of the set around. So like a planet orbits the sun, you take some particular thing here, you think of it as a planet, some object, and when you hit it with the group G, all the different elements of G, it moves it around and it orbits around this collection of elements. And it visits each of these elements here, and it only visits these ones. It never pops out here. So this X just orbits around here. Okay. And any of the other elements here, the orbit of this one is this collection of elements too.
So are they all the same in that orbit?
They're all equivalent. They're different elements of the set X, but they're equivalent. Meaning you can move from one to the other by hitting that with a group element. So you think of it like a dynamic process. There's all the elements of the set X sitting there. If I pick a particular element, little g, from the group, I act on every element there. It moves them all around, but they only move around within their orbits. So this X will only move to something else in its orbit. Because the orbit is by definition all the things it moves around through under action from elements of the group G. Okay,
Yeah.
Yeah? And these orbits partition X. They are the equivalence classes under the equivalence relation, so they partition X. So in other words, we can write expressions like this. X is equal to the union, so this is like a big union operator, like a big summation operator. The union over every element little x in the set X, the union of all the orbits. Okay, so those are orbits. Yeah, so let's look at this example 14.7, just illustrates this. So this is a permutation example. So G is a group of permutations. You see here the various labels 1 through 5. So this is like a subgroup of S5, subgroup of the full permutation group on 5 elements, S5. I mean, we'll take it for granted that it is a group. It is closed under the operation and all the inverses are there. So this is acting naturally on the set of elements 1 through 5, the 5 labels, and it moves them around. So, okay, it's claimed here that the orbits, well, the orbit of 1 is the same as the orbit of 2 is the same as the orbit of 3, and that orbit is the 3 elements, 1, 2, 3. So to verify that, you can see, well, okay, you take the label 1, where does the label 1 travel to under multiplication by any of these permutations, or under application of any of those permutations? Well, this one on the very end sends 1 to 3. This one sends 1 to 2. That one fixes 1, sends 1 to 1. That one sends 1 to 3. That one sends 1 to 2. That one, the identity, that fixes 1 as well. So I only ever mentioned 1, 2, 3 there as possible images of 1. So that means 1, 2, and 3 make up the orbit of 1. Because it's an equivalence relation, I don't have to bother to separately calculate what's the orbit of 2 and what's the orbit of 3, because I know it's an equivalence relation. So any of these other things in that same set, they have the same orbit. They just go through the same set of elements. What's the orbit of 4? What's the orbit of 5? Well, you take 4, say, and look at where you can get to by application of any of these permutations. For this rightmost one here, 4 gets sent to 5. This one here, 4 gets sent to 5 as well. That one there, 4 gets sent to 5. That one doesn't mention 4, so it fixes 4 by convention. 4 gets sent to 4. That one, same thing, 4 gets sent to 4. The identity, same thing, 4 gets sent to 4. So I only ever mentioned 4 and 5 as images of 4. So that's all that's in the orbit of 4. And that's the same as the orbit of 5 because it's in the orbit. If you're in the orbit, you have the same orbit as that. Yeah. So that's a nice example. So the orbits give you the structure in the set X. Yeah, associated to the group action, we have this decomposition of the set X into the orbits. And that's going to be a crucial idea, especially when we're looking at the operation of a group on itself by conjugation. It's going to give us a nice, interesting way to decompose the group into subsets. The next thing becomes is two more definitions: fixed point set and stabilizers. Two more definitions. Okay, the orbit is something you associate to an element in the set X. The fixed set X sub G, so this is something associated to an element from the group. and it's a subset of X, it's this subset of X. It's the set of everything in X which is fixed by X. Okay. So remember, the action of the group G on X means that when you take any particular little G, you've got a function of the set X to itself. Okay, in general, you think of that moving the elements of X around, but there may be cases where when you apply G to one of these elements, it just stays at X. G of X equals X. That certainly happens all the time for the identity element, E. It sends every X to itself. But for other more general group elements, some elements in the set X it may move around, other elements it may fix. So we collect all those together into the set XG, the fixed set of G. Okay? So it's a subset of X associated to a particular element, little g. For instance, let's look back at that example we just looked at. This action here. So here are the 1, 2, 3, 4, 5, 6 group elements. Let's look at the fixed set of each of them. So the identity. What's the fixed set of the identity? So it's the elements in the set X that are fixed by that. Well, that's everything. Property 1 says EX equals X for all X. So the fixed set of the identity is all of X. What's the fixed set of 1, 2, 3? This cycle. Well, it's certainly not it doesn't contain any of the labels 1, 2, and 3, because when you act on the elements of X with this permutation, 1, 2, and 3 get moved around. But 4 and 5 don't. This fixes 4 and it fixes 5. So the fixed set of this element here is the set consisting of 4 and 5. Yeah? Similarly, for 1 through 2, that also got the same fixed set, 4 and 5. For 5, the fixed set of that cycle, set containing 1, 2, and 3. Okay? Because 4 and 5, it swaps position, so it does move those. 1, 2, and 3 of these. And these last two, they have empty fixed set. Okay? Because these last two, they move all 5 elements around in various ways. No element is left fixed by the action of any of these group elements. We've got 2 examples of empty fixed set. One example of where the fixed set is all of X, and then some examples where it's a proper subset. Okay. Fixed set will be a useful device, which we'll refer to in due course. So again, that's a subset of the set X we're acting on. So also associated to a group action, we can have meaningful subsets of the group. Now, what do I really mean by meaningful subsets of the group? What are the meaningful subsets of the group?
Non-empty ones.
Non-empty ones, yeah. But not just any of what the subsets we like to talk about is not just any old subsets, but subgroups. Ones that actually have the structure of a little group inside the big group. Those are the interesting ones. I mean, we can randomly just pick out elements and form a subset of the group, but of particular interest are the subgroups. So there is a very natural way to associate a subgroup to this picture. Okay. Then so for any X, and it's associated to, and it kind of mirrors in some way the idea of the fixed set. So the fixed set is a subset of X associated to an element of the group. The stabilizer goes the other way. So for any element of the set X, the stabilizer, and you see how it's mirroring this notation here. So the fixed set is a subset of X, it's X sub G. Stabilizer is associated to an element little x, but but it's a subset of the group, so it's G sub X. Exactly flipping the roles around. So the stabilizer of X is I'll just call it a subset for now, because it's a theorem or a result that it's a subgroup. But what is it? It's the set of every group element that, well, what's the idea of the word stabilizer? Stabilizers on a kid's bike stop the bike from falling over. They stop the bike from changing. So stabilizer is something that doesn't change the thing. It leaves it stable. So in other words, a stabilizing element of the element little x is a group element that doesn't move x. G of x equals x. So let's jump straight to proposition 14.10. This is actually a subgroup. At the moment, looking at its definition, it just appears to be a subset of G. Just by definition, it's a subset of G. But it's actually a subgroup. So G acting on X, G acting on X. If X is any group element, if X is any element of the set X, then G of X is a subgroup. Stabilizer G sub X is a subgroup. Subgroup of G. Proof. What kinds of things could possibly be involved in this proof? Okay. Definition of what the stabilizer is. So referencing back to this definition. And the properties of the group action. Numbers 1 and 2 from the board there. And maybe some very basic things about the group. Just really about how the group operation works. Associativity, inverses, and so on from the group. Okay, think a little bit. We're trying to prove that a certain subset is a subgroup. What do you have to establish to do that? There was a couple of theorems. Well, by definition, a subgroup is a subset which acts as a group using the same operation from the containing group G. That gives potentially 4 conditions you have to prove: identity, associativity, closure, and existence of inverses. You can boil those down. We don't actually have to prove associativity, because if associativity is true on G, it's also going to be true on any other subset. So the 3 things you have to show is we need to show that the identity element, E, is an element of the stabilizer. We need to show the stabilizer is closed under the operation in the group, and that Gx contains all necessary inverses. These are the 3 things we have to show the subset is a subgroup. There was another little result which kind of tried to concentrate these conditions down. It was enough to show that the subset was non-empty, and that this kind of mixture of closure and inverses condition for any AB in the subset, AB inverse was also in the subset. Well, that was a bit of it's a bit like a cheat or a trick. It's trying to squash these conditions down too much. I prefer to just keep it. So these are quite close to the group axioms. These are really just the 3 group axioms apart from associativity, which is automatically going to be true on any subset of the set G. So first of all, let's take them in order. Is the identity in this stabilizer?
Yes.
Yes. Why? Because number 1, it's the definition. It's declared in order to be called a group action, and G is acting on X, has to be that EX is equal to X. So by definition, of group action, E is always going to be an element of X, so it's stabilizer. No debate. Okay. Closure. There's some elements of GX, at least the identity is in there. So now we can ask, let's assume we've got two elements, a G1 and a G2 in the stabilizer. Okay, the question is, we're trying to prove that the product of them is in the stabilizer. That's what closure means. Take any two elements in the subset, their product must be in the subset. Because we want this to act like a group, so we can do this bridging the gap thing. It implies here, we want to show that the product G1, G2 is in the stabilizer. That's what we want to show. Closure, you can kind of just roll this all the way back, I think. What does it mean to be in the stabilizer? We'll look at the definition of stabilizer. To be in the stabilizer means you stabilize the element little x. So we want to show that G1, G2, that element applied to x is equal to x. Well, we know up here, we know G2x is equal to x, because G2 is in the stabilizer. So that would imply that G1 times G2 of x is equal to G1 of x, but that's equal to x, because G1 is in the stabilizer. And yeah. So those two are true since G1 and G2 are in the stabilizer. G2 stabilizes x, so when you apply G1 to G2x, you're applying G1 to x. G1 stabilizes x, so that's just equal to x. And then you can see what the next jump is. Here I've got G1 applied to G2 of x. The property 2 tells us that's exactly the single element G1, G2 applied to x. Okay. So the justification for this movement to this line is by definition of action. So if you take any two elements in the stabilizer, their product is in the stabilizer. Good. So now we need inverses. So we assume G1 is an element of G. We want to conclude G1 inverse is in G. And this bridging the gap. You can only conclude that G1 inverse is in G if G1 inverse of x is x. Well, we kind of proved that already when we were proving the reflexivity of this relation. We all remember we had gx equals y, and then you could say x equals g inverse of y. So if G1 is in the stabilizer, g sub x, that means gx equals x. Well, that implies g inverse x. G1 inverse times x equals x. C, proof of reflexivity above. In the proof of reflexivity, we showed that if gx equals y, that implied that x was g inverse times y. So here we're just using it in case we got gx equals x, and x is going to be g inverse times x. So this stabilizer subset is acting exactly like a subgroup because it contains the identity, closed under the group operation, and it contains inverses, all the necessary inverses. If there's an element in the stabilizer, the inverse of that element is also in the stabilizer. So it's a subgroup. Okay. So for any little x, g sub x is a subgroup. Subgroup of G. Could be all of G, could be nothing but the identity, or it could be some intermediate proper subset. Okay, I think that's where I want to finish. I don't want to go too fast and rush pushing through this. We will maybe look at the statement of the next result. We'll prove it next time, or I'll leave you to read it in the meantime. I'm thinking actually this, instead of the lab on Friday, I think we might do another class on Friday, just to advance this stuff a bit more. I'll arrange a room and I'll send you an email about it, okay? So quite nicely here, so we've introduced orbits and stabilizers. Orbit is a subset of the set X. Stabilizer is a subgroup in the set G. Proposition 14.11 establishes a good, strong connection between the two. This is the order of the orbit, the number of things in the orbit, the size of the orbit. Remember this notation, this was the index of Gx in G. You can form this for any subgroup of a group G. Now the index of a subgroup in G, what this means is this equals the number of cosets of Gx in G, which in the case of finite groups reduces quite simply, it's just the quotient of the sizes. But it only makes sense to talk about that ratio if G is finite. You can still talk about the index of a subgroup, even in the case of an infinite groups. If the group G is infinite, it could still be that the index of a subgroup is finite. It would just be if you talk about an infinite subgroup, then there might only be a finite number of cosets. But in the case of a finite group, this thing we're talking about here is the number of cosets of the subgroup in the group G. If you think back to Lagrange's theorem, every coset has the same number of elements in it. So the number of things is simply the quotient, the size of the actual group divided by the size of the subgroup. Okay. It's not immediately obvious that this is true, certainly. You know, there's a nice little proof there. Yeah, which we'll discuss next time. But I think that's a good place to. Okay. So I'll book an alternative room for Friday.